Okay, so today we're going to talk about the last type of bonding. So far, we've talked about ionic bonding and covalent bonding, and now we're going to talk about metallic bonding. Just a quick recap, ionic bonding involves a metal and a nonmetal, typically, and or any type of ions. And covalent bonding only involves nonmetals. Can you guess what type of elements are involved with metallic bonding? So, metals are the only elements involved in metallic bonding. And this illustration essentially shows what happens in metallic bonding. These little red dots are the electrons that are around the atoms. And as you already know, metals like to give up electrons. So, in this diagram, you can see the electrons that are zipping around all of the metals because it's kind of like playing a game of hot potato. They've given up the valence electron and they're just like passing it around to everybody. And so, how does this game of hot potato with electrons explain the properties of metals? A lot of you actually already know what metals are used for typically. So, like if you open up your wall, you'll find a whole bunch of metals and wires. And why is that? Well, this game of hot potato is a large part of the reason why wires are made out of metals. We're going to explore that. So, the idea is that metals lose one or more of their outer valence electrons and they become delocalized. So, what that means is that they're not local to any one single atom, and instead they just move freely throughout the entire metal as a blob, if you will. So, here you'll see like all the cations, because again, metals form cations when they lose electrons. So, the metal is now represented as a positive ion because it lost its negative valence electrons, which are now just kind of zipping around in free space. And these delocalized electrons are free to move throughout the entire metal. And they are held pretty tightly to the cations because negative electrons are attracted to positive ions. Even though it moves freely throughout, it is still attracted overall to the metal. So you could describe this as a valence electrons in a sea of mobile electrons. So the cations are just kind of surrounded by this like fluid electron wave, if you will. And the electrons are not bound to any individual atom. It's just kind of fluid surrounding the cations. And there's a very strong attraction between the ions and the sea because it's the cations positive attracted to the negative electrons. And because of these properties, or rather because of that behavior, it explains the properties of metals, which are that metals have high melting and boiling points, and that's due to the strong attraction between the positive cations and the negative electrons that surround it. So it's hard to melt metal or to boil metal, which makes sense. I would be pretty afraid if I saw my cast iron pan melt before my butter melted. Metals also conduct electricity, which you probably already know this just from your experience. And that's because electricity is just the movement of charge. So, specifically, like in your wires, there are electrons that are zipping in one direction through the wires. So, that is a movement of charge because the negative electrons are going in a direction. And they travel freely through metal because the metal cations are constantly attracting those negative electrons, so they can move really easily, create a current. Metals also conduct heat, which means that they can get hot easily and cool down really easily. Something that is interesting is if you ever touch like aluminum after you take it out of the oven, it's actually surprisingly cool really quickly. And that's only because it conducts heat so well that it can cool off so quickly, because it instantly is like, I will pass on the heat to anything around me. So some metals are better at conducting heat than others. Aluminum seems to do it especially well. In conduction of heat, the heat energy is conducted by the delocalized electrons, and they're transferred throughout the metal structure when they move. So it's the electrons that are moving that heat around. Hardness is the last part, and metals are hard due to the strong electrostatic force of attraction between the ions and the delocalized electrons. So, I mean, most of you, I think, already assume metals are pretty hard. There are softer metals, but for the most part, a lot of metals, at least that you would find naturally in nature, are hard because of their strong electrostatic force of attraction. All right, so metallic properties, the key ones are that they have luster, so that means they're shiny. They're ductile, so they're able to be drawn into wires. And they're malleable, so you can shape them as well. These are really key properties because if they didn't have these three properties, metal industry would lose quite a bit of money. All right, so here you have your cations, the metal ion, and the electron surrounding it. And the electrons actually act kind of like a hinge. So atoms, when you bend a metal, roll over kind of like on the electron itself, which is why you don't really like break the metallic bond. You can just kind of bend it. So overall, metallic solids, these are the characteristics of it. They have electrons that are delocalized among the metals. The attractive force between the cation of the metal and the delocalized electrons are strong. The physical state at room temperature is typically a solid, with the exception of mercury. Mercury is a liquid at room temperature. Used to be used in thermometers. Melting and boiling point of metals is very high. It's hard to melt or boil metal. The solubility in water is not a thing. Metals, for the most part, it's like, can you imagine like a steel suddenly dissolving in metal? All of the bridges would just fall to pieces. So, I mean, thankfully, they're not soluble in water. Otherwise, it would be rather hard to form some solid structures. That being said, there are still metal ions in water, but that's from ionic substances, not from pure metallic substances. Completely different. Electrical conductivity, yes, they are conductive whether they're a solid, liquid, or a gas. Other properties include them being hard, malleable, ductile, and lustrous, shiny. Again, metals are on the left side of the periodic table. They are on this diagram, they're yellow. This pink one is hydrogen, which really should be over here, but because it only has one valence electron, technically fits into group 1 the best. So just really quickly, why does magnesium have a higher melting point than sodium? So again, sodium is right here. They're both in period 3, which means they have the same number of electron shells, except sodium is in group 1, so it only has one valence electron. Magnesium is in group 2, so it has two valence electrons, and it also means it has an extra proton in its nucleus. So Magnesium has more electrons in its valence shell. It has 2. Both of these electrons become delocalized, so the C has twice the number of electrons per atom than sodium, which means they're going to be a lot more attracted because there's more negative to be attracted to a greater positive cation, which is important. The remaining +2 ions have twice the charge, and therefore there is a greater electrostatic attraction between the ions and the C. Each magnesium atom has 1 more proton in the nucleus compared to sodium, and therefore this extra proton results in a greater attraction for the delocalized electrons. And magnesium atoms have a greater atomic radius, and so the delocalized electrons are actually closer to the nuclei, increasing the electrostatic attraction. All right. So that is the essence of metallic bonds. And that is the third type of bonding that we have learned about. Again, so far we have now talked about all 3 major types of bonds, including ionic, covalent, and metallic.